Yes, a good afternoon. Is it a good afternoon? Hopefully, yes. Last time we looked at inverse trig functions. We looked at differentiation of inverse trig functions, and we had a smooth flowing lesson. Today we will look at, I left here an exercise, yes? Exercise until I get a feedback. But I told you that there are terms that have differentiation, the ones we call logarithmic differentiation. And pick that topic from where it should have started. Further differentiation. If you have Backhouse, this is chapter 11. Of course, Backhouse 2. I do not recommend S5s to follow this lesson for now. If they follow and they do not pick things easily, they should not blame me. Even if they followed the questions we are discussing, they will not meet them until they are in S6 probably, unless their teachers do teach topics through Backhouse 1, continue to Backhouse 2. Otherwise, I want us to deliberate this lesson of close to 1 hour to look at this and any other additional concepts that we may need to look at. So we will begin by looking at what we call logarithmic differentiation. Of course, you are expected to have the concept of differentiation already, given that now but mainly looking at inverse trig functions. We are differentiating once again, but we are saying logarithmic. That means that you are expected to recall, where there is need, the use of logarithm rules. This differentiation that we are calling logarithmic is very powerful. It is a powerful method that can considerably simplify the differentiation of it simplifies the differentiation of two parts. It simplifies the differentiation of one, products and quotients of a number of fractions. And two, it simplifies the differentiation of some exponential functions. And we are going to introduce it best by looking at some properties of logarithms, as I've already said. That's why it's called logarithmic, and how we can differentiate functions of y with respect to x. For example, if we have a question that says that the ln of a cubed times the square root of b all over c squared. We need to be able to know that this can be expressed, knowing that ln is log. It can be expressed as the ln of a cubed plus the ln of b square root minus the ln of c squared. The candidate should already be in the know of the logarithm rule that you can use to simplify this. And we can look at this as 3 ln of a plus a half ln of b minus 2 ln of c. If we already have that knowledge, it makes it easier for us to advance. In other words, we need to first of all be able to simplify a given function in that kind of format. If this is a, they can therefore ask you to write in a similar way a form as the one I've used above, in a similar form, and they give you like ln of a squared b. We are saying since they are multiplying, we can expand by adding, and we can eventually say this is the same as 2 ln of a plus ln of b. There is a full question there with the remaining parts from b up to f. B up to f. The page is 200. You could try out these later. This is a simple to express them in that format. We can look at the second case. They give us a question that log of 10 to the 10,000 is written as the log of 10 to the 10 to the power 4, which we know is 4. Of course, you ought to be reminded that log of 10 is 1. And then there is a question here. They are saying, in a similar way, simplify in a similar way. A similar way. And they give us numbers like log 10 of 1,000. This one, even a good senior 4 student would do it. But in a similar way, we shall say it is 10 to the power 3 of 10, which will definitely be 3 log 10 of 10, which will be 3. And similarly, there are other parts here that you can consider to try out. Parts B up to F again. I have done part A, so you can try out that, just like I did the other bit and I asked you to try out. These areas that I'm saying try out are simple exercises that can strengthen you there. Then we have example 3, where they can say differentiate with respect to x, and they give us a number like ln of x. Ln of x. What do we do here? They say differentiate with respect to x, and they give you ln of x. Now for this number, we will let y be equal to ln of x. But there is one concept which we shall note, that ln is the same as log to the e. So there is a concept here that this implies that e to the power y is equal to x. But we should already be in the know of the derivative of an exponential function. We should already be in the know, otherwise if we will be stuck. Here, you're expected to know that d by dx of e to the power x is e to the power x. You're expected to be knowing this. Meaning that if we have this and want to differentiate e to the power y is equal to x, we shall have e to the power y dy. When we differentiate, it stays the same. Should be equal to dx. This will imply that dy dx, which we want, will actually be equivalent to divide by dx everywhere, will be equivalent to 1 over e to the y. But remember, e to the y is x, so it is 1 out of x. In other words, d by dx of e to the y, or d by dx of ln of x, for that matter, is 1 out of x. Is 1 out of x. In the norm of how that is done. Now, once you know that d by dx of an exponential function is given as that, then we can proceed and move on to the next part. I can give you another number to try out here of the same kind. If that is a, we can look at b and say b is ln into 1 plus 2x. And they say find dy. Find dy by dx. First step I've said, we let y be equal to the ln of 1 plus 2x. But we know ln is the same as. There are several ways. You can choose now to let this, you can choose to let u be equal to 1 plus 2x. You can choose to express it as a log. I will use two methods. Let me use this. If I let u be that, it means that my y is ln of u. And this takes it to be similar to the first case. So I'll get dy here being equal to d by du of ln of u. I want to differentiate to get my dy by du. So dy by du from the previous example where we differentiated ln of x, we shall get this as 1 out of u. You keep it there. From here, you need to get du by dx as well. Du by dx will be equal to 2, since when we differentiate a constant is that. So by chain rule, dy by dx, which we want, will be dy by du times du by dx by chain rule. So we substitute in these two, and we shall get dy by du, which is 1 out of u, times du by dx, which is 2 over u. But we know u. Therefore, we can conclude and say that dy by dx will be 2 over 1 plus 2x. In other words, d by dx of ln of 1 plus 2x will be equal to 2 over 1 plus 2x. In other words, in summary, I can say that if you are differentiating this, differentiate the interior to get and divide by that. In that question, I have done part A and part B. This is part B. I can still go ahead and say you will have to try out part C to F. There. We proceed to another part where we will yet learn how to differentiate another. By chain rule, note here that differentiating functions of y with respect to x, we have been differentiating functions of y with respect to x, we can easily find if we need to use the chain rule. Like I've just used the chain rule, it is possible to use that. But like I was saying, maybe I can give you the second method for the above number, method 2. Like I said, you can express this as the log to the e of 1 plus 2x. This will give us e to the y being equal to 1 plus 2x. So if we input both sides, since we have noted that that d by dx, for example, of e to the x is x, this one we recall. If you recall that this is true, then it means d by dy of e to the y will give us d by dx of 1 plus 2x. So it means that we shall get e to the y dy, if we differentiate, will be equal to 2 dx. And we want to get y by dx. So divide by e to the y dx on both sides. And we shall get that dy by dx is actually 2 over e to the y. But what is e to the y? But e to the y is known as 1 plus 2x. Therefore, your dy by dx becomes 2 over 1 plus 2x, as already obtained in another method. So there are several methods that one can employ. We can employ the chain rule by substitution, and we can use that to still be able to get that method. We will proceed to look at, assuming that this time you are differentiating y, you are given another function. Consider a function like that z is equal to y to the power 4, and they tell you to find dy dx. Find dy dx, but they have given you that. Okay, here you'll find dz dx. By chain rule, we know that dz dx will be the same as dz dy times dy dx by chain rule. If you are given a number like that, it means we are going to get dz dy, which will be 4y cubed. So dz dx, if it is 1 required, will be equal to dz dy times dy by dx. And this will be equal to our 4y cubed times dy by dx. So you say that your dz dx in this case will actually be equivalent to 4y cubed dy dx. So you can be given the numbers and say differentiate with respect to x, and they give you a number like 3y squared. 3y squared. We are saying we have been letting y equal to. Now you must let another letter, and we have chosen that we can use z. Let z be equal to 3y squared. So get dz dy, which will be 3 times 2y, which is 6y. So go ahead to get dy dx, dz dx will be therefore equal to dy dz, dz dy times dy dx. So it means that our final answer, dz dx, will be equal to our dz dy, which is 6y, times dy dx. Numbers of this nature, you should be able to do them. Numbers of this nature, you should be able to do them. And again, if you look at question 4, the page is now 201. You can try out parts B, C, and D. Try out those ones using that approach. We can look at another example. These examples are all unique. We can look at another question where they are telling us to differentiate. Differentiate, and you're given a number like e to the x squared root of the sine of x over 2x plus 1 cubed. Now the concept of differentiation is the same throughout. When we are given a function in x, we usually want to get dy dx. If you are given a function in z, in y, you must introduce another function which is not x. That's why we are using z up here. And we are actually looking for z dx, even when x is not part of the function given. Here, if it is purely in x, then we will let y to be equal to that function. X squared, the square root of the sine of x, over 2x plus 1 cubed is our y. And now, if we let this be the case, remember that we are looking at logarithmic functions. Logarithmic functions. We will have to introduce the natural log. Introduce the natural log on both sides. We say the natural log will make such differentiations easy. Introduce the natural log. And let this be ln of y being equal to ln of x squared root of the sine of x over the 2x plus 1 cubed. And then after introducing this, we apply what the interpretation of the log rule dictates here. So our ln of y will definitely be equal to the ln of e to the x squared. Since we are multiplying, we add, plus the ln of the root of sine of x. And we take away, from here the denominator, the ln of the denominator, 2x plus 1 cubed. We go ahead to say that this will be equal to the ln of. Now, one thing we should understand here is this is the natural log. In words, natural log of e of x squared, implying therefore it is actually supposed to be just x squared. I have put this there for you to be able to quickly see, but I will leave the rest for now the way they are and say this will be the ln of the sine of x, also the power half, minus, this is clear, I can write it as 3 the ln of 2x plus 1. This half is going to come here, and this x squared is going to come out. Plus a half ln of sine of x minus 3 ln of 2x plus 1. Remember that all this is equal to the ln of y. Now, with the first experience we had with the differentiation of ln, we saw that the derivative of ln of x is the same as 1 of x. The same as 1 of x. And remember, we want to get the ln of, we want to get dy by dx of that expression. So once we know that it is now with the differentiation of ln, we recall that d by dx of ln of x is actually equal to 1 out of x. We already know that. That is where we started. If you still remember where we started today, then it is very clear that we can now say, I think we should still have that information I'm talking about. Let me see, yeah. Right here, look at this. d dx of ln of x is 1 over x. So once we know that that is where we started, it implies that if I take the step we have and I want to differentiate, I now have my ln of y is equal to x squared plus a half ln of the sine of x minus 3 ln of 2x plus 1. And our task is to get the derivative. We want to differentiate with respect to x. What happens? Here I'll get 1 out of y dy, because we already know that dy of ln of y is 1 out of y. So 1 out of y dy should be equal to, when we differentiate this, we shall get to x. When we differentiate this, we should be able to know that d by dx of ln of sine of x should be equal to, I don't know whether it is clear that you see this, but we already looked at differentiation of trig functions. D by dx of cos of x is equal to negative sine of x, and d by dx of sine of x is equal to cos of x. So if we differentiate this, since we know that it is a natural log, it will give us the cos. The derivative of sine gives us cos. So it will have that 1 over cos. D by of the ln will give us that. But if we take it as, let me emphasize this, if I let my ln be written as log of e of sine of x, for example, and I equate it to y as a simpler number, it means my e to the y is equal to the sine of x. I want to get the derivative of this. So d by dx, which is supposed to be dy by dx, is going to give me e to the y dy will be equal to, when I differentiate this, I will get cos x, cos of x, so dx of sine is cos. But I want to get dy by dx. So my dy by dx here, if I make x over e y over ey, but my ey is sine x, so it means that if we differentiate this, which we have here, we will get cos x over sine x. So it means here I'll have the cos of x over the sine of x, then minus, this will be 3 times, we said we differentiate the numerator and we divide by what we have. That is what we shall have there. So if I move it to the lower step, this was just to emphasize how we differentiate that, and the whole of this is subjected to a dx. It's subjected to a dx, such that if I divide, I can have 1 over y dy dx will now be equivalent to my 2x plus a half cos x over sine x minus 6 over 2x plus 1. And if I want to get my dy dx, I can now say that my dy dx therefore is equal to y into the whole of my 2x plus cos x over 2 sin x minus 6 over 2x plus 1. But my y is known from up there. My y is known. I'll say, but my y was e to the x squared, the sine root of sine of x over my, and therefore I can conclude and say that my y dx will actually be given by my y, original y, over 2x plus 1 cubed, or into 2x plus cos x over 2 sin x minus 6 over 2x plus 1. And this becomes the derivative of that seemingly small expression we had. It becomes the derivative, but we can take it an extra mile and expand it and simplify it. And when we expand it and simplify it, we will definitely get another bigger value out of it. If we simplify it, it can go to another step. If we want it simplified, we could proceed to take it another mile. We could proceed to take it another mile by taking the LCM in there. If we take the LCM and we pull it out, the LCM will be 2x plus 1 times 2 sine of x. If we pull it out, we can use thirds here to reconcile the sign, and we shall get a whole expression simplifying to a different final answer. So you can simplify it in your free time and see how can you simplify it so that you pull out a common factor and you rearrange it. Because when we make this the LCM, this term here will be part of the LCM and it is similar to this term. So if you pull it out, this will raise the power 4. If we pull out that 2 will come out also. It will be part of the LCM. And this sign will come out. But when this sign comes out and this one, they are treated as indices. This is the power half, this is the power 1. So if this rises down, it will come to the negative half and it will make this become a root of sine. So if we do that, actually you are supposed to simplify to show this. To show that you will stay with that, and down you will have these 2, and you will have the root of sine of x, and you will have 2x plus 1, the power 4. These ones can be clearly seen. They can be clearly seen straight away. Because when we take this with a sign, it goes down to give you this. This 2 is that one. This one, when we pull it out, it gives the 4. Now, you will have the other struggle is to show what stays inside here. Because now we'll have our 2, which should be subjected to both this. 2 sin x into 2x plus 1, then plus cos of x, subjected to 2 into x plus 1, then minus 6 subjected to 2 sin x. And you simplify that until here. The denominator is already out. So you can simplify to show that bit. And there is another trial exercise here. I've given you many tries, but this will be the exercises. Question 5. Question 5 is on page. The page is now 201. It has parts A, B, and C. And they are telling you, use the method of the first example to differentiate. Use the method of the first example to differentiate. I will try to lead you through one. Part A. They are saying try to differentiate, and they are saying this is root x plus 1 over x minus 1. So we said we will let y be equal to this x plus 1, x minus 1. This should be able to guide you to try out the other. But this can be written as, you notice it is the cube root, the power third. So if we take natural logs on both sides, it means we are saying that the ln of y is actually equal to the ln of the other side, x plus 1 over x minus 1 to the power third. And our ln of y will definitely be equal to x plus 1 to the power third, If you recall that a over b to the power n is the same as a to the power n divided by b to the power n. And since we have logarithms that we are dividing, we subtract. So our ln of y is ideally the same as a third ln of x plus 1 minus a third ln of x minus 1. And our task is now to differentiate that. Our task is to differentiate that. We say that we shall get 1 over y. The y will be equal to a third. We differentiate this, and the easier differentiation there is differentiate the numerator, the bracketed term, and divide by the bracketed term. Minus a third times differentiate that, you get 1, divide by the bracketed term. This is ideally what we get, and all this is with respect to dx. So our dy dx in a nutshell becomes y times the whole of this, a third into x plus 1 minus a third into x minus 1. But since y is known as this, then y by dx x plus 1 the power third over x minus 1 the power third into 1 out of 3 minus 1 out of 3 into x minus 1. We can simplify this by pulling out a third, as I told you with the previous number. We will have our x plus 1 the power third over x minus 1 the power third. Let me first reconcile this. The LCM will be 3 into x, I can say plus 1 into x minus 1. And here we shall have, when the whole of this is divided here, we will actually get x minus 1. Minus, when the whole of this is divided here, we get x plus 1. And when we reconcile the bracketed numerator, we shall get negative 2. So we shall have, keeping this here so that you can see how it affects. When I pull everything out, the denominator, I'll have this, the power third, times x minus 1 times x plus 1 times 3 into, now this should be negative 2. Okay, x minus 1 minus x minus 1. The denominator has been pulled out. The x will cancel here, and even this I am going to take it down to merge with this, and this will merge with this. So I'll get negative 2, sorry. I'm moving towards my final answer, over 3 into x minus 1. This will rise by 1. So it will be 1 plus a third, which is supposed to ideally be 4 out of 3 into x plus 1. This is a power 1. This will come down and will be a subtraction. 1 minus a third, and that will be minus 2/3. 1 minus a third is 3, is it should be a positive, is 2/3 positive. This will be our dy by dx. So I want to challenge you to use that approach to do the other parts of question 5, part B and C on page 201. I will move to the last bit of this discussion. Maybe we shall try out 2 more numbers, and you will be pushed to look at exercise 11A, which I had pushed you to last time. Yes. There is another question here. They tell you to differentiate, and they give you a number like 10 to the power x with respect to x. With respect to x, we have said that you let y be equal to the number they are giving you. Let y be equal to the number they are giving you. Introduce natural logs. Introduce what? Natural logs. Natural logs. If you introduce natural logs, you'll have ln of y being equal to ln of 10 to the x. We have said with natural logs, well aware of this rule that a to the power x base c is the same as x log sc. Our ln of y will definitely be equal to x ln of 10 for this case. Our ln of y will be equal to x ln of 10. Now the following step is differentiating. If we differentiate this side, we'll get 1 over y dy. And if we differentiate this side, we'll get ln of 10 dx. It is like, this is like if you have 5x and they're saying differentiate, it simply becomes 5, but dx. We don't treat this as a product rule because we have only a coefficient, or a term that is a coefficient of x, has a coefficient of x, which is ln of 10. So our dy by dx here will actually be the same as y ln of 10. But what is our y? We know our y. So our dy by dx will be our 10 to the power x ln of 10. Ln of 10. We can look at the last example for today's discussion. The last example is differentiate with respect to x. Differentiate, we can look at 2 examples. Differentiate with respect to x, these are short examples. They give you a number like 2x squared. 2x squared. Of course, we still let y be equal to what they have given us. But this has 2 approaches once again. So let's introduce the ln. The ln will make it much faster and easier. If we introduce the ln, it gets us to ln of y being equal to ln of 2x squared. And this means that ln of y gets this to x squared ln of 2. Which makes it easier for us now, because we already know that ln of y is the same as 1 over y dy, and this is just like the other one, that we are going to differentiate the term in x to give us 2x, and this will stay. And ultimately, this will be having a dx there. So our dy by dx will automatically become y times 2x ln of 2. We feed back the value of y, and we state our final answer as 2. Now it would be 2 x times 2x squared ln of 2. This will be the answer. But I want to show you an alternative. The alternative one would be, someone would say, let y be equal to 2x squared, and further let u be equal to x squared, such that y is equal to 2 to the power u, but u is x squared. So this person will get the y. We have already seen that when we differentiate 10 to the power x, for example, we got this. So dy by du will be the same as, will be the same as 2 to the power u ln of 2. Take note of that. And now du by the x will be 2x. So by chain rule, dy by the x will be dy by du times du by the x. And if you substitute, you'll still get the final answer as dy by du, which is 2u ln of 2 times du by the x, which is 2x. When we substitute for u again, our dy by the x alternatively will give us 2x. I'm writing this 2x first, times 2 to the power u is x squared, ln of 2, which is still giving us the same answer. That is another alternative. This is not provided for in Backhouse. This is the method they are giving you. But this, as you notice, arrives us at the same answer. Lastly, there is another part here. Say differentiate x to the power x, x to the power x. As we have said, we let y be equal to x to the power x, and we take natural logs. If we take natural logs, ln of y is ln of x to the power x. Now, this is what happens. If we differentiate this, we have already seen we get 1 over y. And this is the same as, by the way, as x ln of x. Now, in this case, you consider this as the product rule. One becomes a u and one becomes a v, because they are all terms in x. So we'll have v, which is ln of x, times du dx, which is 1, plus u times dv dx, which is 1 over x, or is subjected to dx here, if we have not brought it there. So 1 over y dy now becomes 1 plus ln of x dx, because this would be 1. And therefore, the final answer, y dx, will be y into 1 plus ln of x, which you can write as, when we bring in the value for y, we can conclude and say y dx, therefore, is x to the power x into 1 plus ln of x. Yeah. So, next meeting, we will also consider in the bit of integration by inspection method. By inspection method, which we can call trial method. How do we integrate terms that have inverse functions? But I want to continue focusing you on exercise 11a. Exercise 11a will still be our focus for now. Exercise 11a will still be our focus. When we meet tomorrow, if we are doing maths, we shall proceed to look at the next part, such that you are enabled to look at the trial, at the miscellaneous exercise, such that you are enabled to look at the miscellaneous exercise, and we shall then be able to move into differential equations. Because we have now the knowledge of differentiation, we shall proceed to move to differential equations. I want to wish you a good day. We declared to have an interaction time between midday and and 1. And because this lesson started a bit late, we still have that interaction there. If you have any queries on the pending work, I will be accessible to guide you on the solutions you've got or where you are challenged, especially with the previous work, not today's work, but the previous work. Have a nice time. Continue practicing, because it is the only way. It's the only way that we can improve, especially with science areas. God bless you.